In this video, we're going to be talking about capacitors. Now, it is written on the board, and here's the diagram as well to illustrate what a capacitor looks like. Okay, now, first things first, what is a capacitor? Now, a capacitor is simply a device that helps to store charge. So, basically, what the capacitor does is that it helps to what? Store electrical charges. Okay, now there are various examples of types of capacitors that you find around. Okay, but the primary purpose of each of them is still to store charge, and this diagram gives the basics of those different examples or types of capacitors they are going to find in any textbook or materials or anywhere. Okay, now a very good example or a very common example you find as a capacitor is most likely or most times materials or devices around you. A very good example might be what you're thinking of. What is the battery? Okay, a battery is a device that stores charge, okay, and later dispenses it when we are ready to use it. Okay, so that is what a battery does, and a battery is a very good example of a capacitor. Now, here is the setup for a capacitor. We're having a voltage having a positive and negative sign, okay, that is a DC voltage, and then it is connected to one plate, and then the negative side is connected to another plate. So you can see there is a plate under spaced at a distance d, okay, and there is a plate on top. Okay, now this plate on top is having a positive charge, that is why you can see it is connected to the positive plate, and this one a negative charge of which is connected to the negative plate. Now the distance, these plates they are not touching, okay, the distance between these two plates is just air or space. In this case diagram we're having, like I said, we're going to use this diagram to tell us or to make you understand about other capacitors that do not have spaces, or they might as well have spaces between them. Okay, now this space or materials that are placed in between these plates, they are called dielectrics. Okay, so materials that are placed between two positive or rather a positive and a negative plate, they are called what now? Dielectric. A dielectric is simply a material that is placed in a capacitor between the plates. The dielectric could be air or free space, which you are having in this case, or sometimes it could be chemical compound as well. Okay, now what we notice for a setup like this is that as the potential difference is applied across the plates, what we notice is that there is a build-up of electric field between the plates because there is a positive and a negative charge. Remember, the positive sign and the negative sign is going to tell us the direction of the electric field, in the sense that the electric field will move from the positive charge to the negative charge. Okay, that is, it will be moving down in this case. We would have positive upward, negative upward, like in this case, or would have a minus here and a plus here. It doesn't really change anything. Okay, now the electric field will move from the top to the bottom because of the way the charge are situated. Now, as the electric field increases with time, okay, or rather the electric field, we notice that it increases because of the number of charges that increases or accumulates at these plates after a period of time in which they be connected to a voltage source. Okay, so the electric field, you notice that it's built up as the charges increases. So we can see that the electric field intensity, which represents the amount of electric field lines you can find in there, okay, it increases, or we can say it's directly proportional to the charge. So as the charge increases, it increases as well. Okay, now why does Q increase as well after a time t? Okay, this is simply because V has been connected to these two plates, and as the value of V reduces here, the value of V increases here. Okay, so the value of E will depend on the value of Q. On the other hand, Q is going to depend on the value of V. Okay, so as E increases, it is due to the value of Q that is increasing. Okay, and the value of Q is going to increase due to the potential difference between the plates, not this one. Okay, now at a certain point, this one starts giving us charges, okay, to a lower potential point. Okay, why does it do that? This part, this two plates, they are initially at a potential difference of 0, and this one is, let's say, fully charged. So what will happen is it will have to give out charges just to make sure they are equal in value. So let's say the final value now becomes VAB. So the potential difference here will also be VAB. Okay, now the potential difference at this point starts increasing, okay, causing the number of charges to what now increase as well. So we can see that the charge will increase due to the potential difference or the build-up between these two plates. Hence, we can as well say that Q is directly proportional to V. Okay, this means that as the potential difference increases between the plates, there is more charge that is being accumulated between the plates. Okay, now we can bring in a constant. Remember variation in mathematics, bringing in a constant, we're going to get Q is equal to CV. I'm making C the constant in this case. Now there is a reason why I did not put K. I represented it as C instead. You can choose to do it any way you want. Okay, but then we're talking about capacitors, so it will be better or more understandable for us to make use of C. Now this C has a name and it is called the capacitance. Okay, I'm going to write it out and it is called the capacitance. Now what the capacitance does is or in this case, in this equation, it is simply a constant between these two guys. Okay, now the capacitance, it is simply the ability for this whole capacitor to store charge, or the capacity for it to store charge. A similar definition to energy. Okay, so the ability for it to store charge is what we call what now capacitance, or most times we refer to this as the capacitance of a capacitor. So by making C the formula from this equation, we're going to have something like C is equal to Q over V. Now we notice from here that C, after being made the dependent variable equals Q over V, we cannot define C in accordance to the equation we're having here. Okay, now C cannot be defined as the ratio of charge in a capacitor to the potential difference that is applied to it. Okay, so the capacitance will consider directly proportional to the charge that is being put there, okay, and the voltage, of which you know as this increases together, what happens is that C becomes constant. Okay, so C is constant for every capacitor that we are having. Okay, so capacitance of a capacitor can now be defined as the ratio of electric charge between the capacitor plates, okay, to the potential difference or the voltage that is being applied. Now, the capacitance of a capacitor depends on other properties, okay? It depends on the geometry of the capacitor. When we talk about geometry, we talk about the size, we talk about the distance between the plates, and stuff like that, okay? That is what the capacitor depends on. Now, to do that, we still have to play with one or two more equations to see how this is being gotten, okay? And see how true it is. I'm going to move to this other side of the board. Okay, now there is something we have to take note of. Remember from our Gauss law, okay, we did say that from our Gauss law, the net electric flux in a closed surface or in an enclosed surface was equal to the line integral of the electric field intensity with respect to the area. Okay, we also said that it is equal to the net or enclosed charge divided by the permittivity of free space. That was what we said, right? Now, if this equation is true, we also prove that by integrating this guy along a closed surface, we're going to get E times A equals Q over permittivity of free space. Okay, that's what we're going to get. EA equals Q divided by the permittivity of free space. Now, we want to see how we can substitute these values into what we're having here. Okay, now, from electric field intensity and electric potential, if you've not watched this video, I'd advise you to watch those ones as well. Okay, that's still on our playlist. Okay, you can watch this video to get a great idea of electric field intensity and electric potential or voltage as well. Okay, now electric field intensity and electric potential, they do have a relationship, of which you know that the electric field intensity is equal to the electric potential divided by the distance between a plate or two surfaces, okay, having electric fields between them. So the electric field between these plates is equal to the electric potential, okay, divided by the distance between the plates as well. Now let's see how we can actually manipulate these guys and then substitute into C, okay. So what we're going to get, so if we substitute for E in this equation, we're going to get V over D times A equals Q divided by permittivity of free space. Now I can choose to make V the subject formula in this case as well, okay, by cross multiplying. I'm going to get V is equal to Q times D divided by A times permittivity of free space, right? Now how about we try substituting this formula into this one? So I'm going to call this equation 1 and I'm going to call this equation 2. So I can come here and then say substituting, okay, we're going to substitute equation 2 into equation 1. Okay, here's our equation 1 and over there is our equation 2. So we want to substitute the value of V into this equation and see what we're going to get. Okay, so C then equals Q, okay, divided by V is QD over A mu naught, right? So we're going to get not mu but rather epsilon naught. Okay, so we're going to get QD divided by A times what now? Permittivity of free space. Of course, we know how to divide this. We know how to work out these things out. So notice that C will then become Q, okay, turning this into multiplication sign. This one becomes reversed, right? So it becomes A E naught over QD rather. So we have A times E naught divided by Q times D. Okay? So from here, what are we going to get? We notice that Q cancels as Q, yeah? And then we're left with C is equal to A times permittivity of free space divided by D. Okay? Now, here is a new formula we also need to take note of. Okay? I'm going to call this equation 3. Now, initially, we said that the capacitance of a capacitor is fixed, okay, for every capacitor. The capacitance, that is, it has a particular value you can store charge up to, okay? And it's usually measured in farads. Now, take note that farad is the basic unit for measuring the capacitance of a capacitor, but we can as well break it down, okay, through using this formula, okay, to get a more simplified unit for us, okay. But the same one we have just that is peculiar to energy instead of Newton meter. We also have what now? Farad, peculiar to what now? The capacitance of a capacitor. Now, the capacitance of a capacitor depends on the area as well as the distance between the plates as well. Okay, now the area we're talking about is the area of this plate. In this case, we're having a rectangle or a square, depending on which one you're saying. Okay, it is not drawn to scale. Now we're having an area, okay, of plates here. We are saying that the bigger the area or the larger the area, the more surface area we're having, the more the tendency for the capacitor to store charge, hence an increase in its capacitance. Okay, so C equals A E naught divided by D. It simply means that the more the area of the place we're having, the more value we're going to get for the capacitance. Okay, now how about the distance between as well? Now for the distance between the plates, as the distance increases, what happens is that the ability for the capacitor to store charge tends to do what? Decrease. Okay, that is something to also take note as well. As the distance between the plates increases, the ability for the capacitor to store charge tends to what now? Decrease. Because obviously, okay, using a normal understanding, you notice that as we pull this plate apart, okay, remember columns of which we've done as well. You can also watch a video on that. As we pull this plate apart, what happens is that the force of attraction between these two plates tends to what now? Decrease. Remember columns law. I'm not going to talk more on that. We already explained that in a different video. Okay. So now here is the formula we just finally derived. C equals A permittivity of free space over D. Now here is actually one of the basic formulas you take note. If this is your first time or you might have done it before but you want to take a quick review on capacitance or capacitors, okay, here is one of the basic formulas you should take note of. Now how about the permittivity of free space? Okay, in this case we're having permittivity of free space, so we are making use of the epsilon naught. Okay, we could as well have permittivity of a particular medium, that is if the capacitor is not having a dielectric to the air, let's say it's having a dielectric to be some other material. Okay, remember I said we could use some chemical compounds. Example, we have ammonium compounds. Okay, we have some derivatives of ammonium that are used as dielectrics between these plates. Okay, so we can see that the capacitor, the capacitance of the capacitor rather depends on the area as well as the distance as well as the permittivity of the medium. In this case, we're having free space. So an increase in permittivity of free space causes an increase in the value of the capacitance. Okay, here is a brief introduction to capacitors, or the study of capacitance of a capacitor. Okay, in our next video we'll be solving a few problems that are related to capacitors. Okay, and if you have a question, please put it in the comment section. Do it to like, share and subscribe to our YouTube channel. Okay, and then click on the notification bell. Most importantly, click on the notification bell. This is because when a new video is being uploaded, you get notified. Okay, now this is case 1 of capacitors. Okay, there will be a case 2 of be solving problems, and I'll use that next video to answer more questions that you might be having. Okay, those pending questions you can as well drop them in the comment section. See you in the next video. Stay tuned.